So I will talk, in this talk, will be mainly focused on the pseudogap to the extreme, because I'm looking at the pseudogap and its relation with superconductivity in the stream of the dome, of the superconducting dome. I will come in detail to this. So I will rather go quickly on my introduction, thanks to the introduction done by my previous speakers. So, okay, we are talking about cuprates, the phase diagram rather rich. Superconducting phase, high temperature, and the pseudogap phase that we have seen is a good metal, perhaps, but is still unconventional. In this sense, I will say bad metal, with the surface, Fermi surface, that breaks into pieces. So for my student that was asking me before, these regions here are called hotspot. And the nodes, conversely, are called cold spots, because hot, you have a high scattering, you lose the Fermi surface. As you can see, sorry, here. All right. So there has been an open, long-standing question about the relationship between the pseudogap phase and superconductivity. And two main philosophies have been fighting over the years. One describes the pseudogap as a competing ordered phase with a quantum critical point buried under the superconducting dome that will give the ITC. Early theories put forward, mainly by Phil Anderson, ascribed the pseudogap to a sort of mother phase of the superconductivity. Pseudogap will be a liquid of already preformed Cooper pairs that will both condense, and then the superconducting state will be essentially the low temperature state of this strange resonating valence bond phase, for example, or preformed liquid phase, and so on. So people have been focusing a lot on the pseudogap, even more than on superconductivity, because there is the idea that to understand the superconducting mechanism, the ITC superconducting mechanism, one has to understand the normal phase underlying the superconducting state. In recent years, more and more people have been discussing about possible competing orders. That's a bit, most of the time, this is the vision that people working in this field is giving you. And people have been looking desperately for this not well-identified order. It's a nice achievement of these recent years that they have found charge density wave under application of magnetic field. Now, if there is no magnetic field, the charge density wave state that you see here is perhaps not stable. It's a short range, short density wave, or so on. But looks really important phase and seems present in all the cuprates family. However, cannot really explain the pseudogap phase, which is, well, more and more people is realizing that here there is a dome-like shape phase. The pseudogap temperature instead is always increasing, so not clear. So people has been looking for other possible orders over the years. There is, for example, the spin density wave order has been put forward as a serious possible theory. Loop currents, if Chandra Varma will have been here, will have talked to you about this possible hidden order. Next year, people will talk about nematicity. You already feel in the air. So let's say that it's not clear, and it's still a very much open question if there is an hidden order or not. Now, this is what I'm going to talk to. Today, I will present theoretical results, actually, and theoretical results obtained mainly with cluster dynamic mean field theory, which is an extension of the dynamic mean field theory you heard so much over these days. One first point is that we don't need an order or need an order to explain a pseudogap phase within this theory. And then I will try to enlighten the relation between the pseudogap and the superconducting state in the extreme points of the superconducting dome. Actually, I will mainly talk about the underdoped side. The overdoped side I will pass quickly because this is mainly experimental work and I just give an interpretation, which is less related to the other part of the talk. And at the end, I will try to, well, not give an answer because it's really very difficult, but put some seed into this question. Can the pseudogap in some way be useful for boosting ITC? We have some new result on that. So to be clear, what I'm doing is studying the Hubbard model in 2 dimensions that we think portrays in a minimal model the copper-oxygen planes that are present in all cuprates. So we have a square lattice in 2 dimensions. The situation which is interesting is the following, where you are close to the Mott insulator, which means you have 1 electron per site. In that case, the interaction, this term U, that is active when you have a double occupation of the sites, kicks in and penalizes enormously the system. So when you have a situation in which U is of the order of the kinetic energy, the system is fighting between leaving 1 particle per site and moving particle around. And that's the interesting and difficult part of the problem. So to solve this kind of problem is very hard because the interaction U does not allow to use simple methods, so standard methods like perturbation theory will break, and mean field, depends which mean field you do, you can get whatever. So we had to do better, and that is where dynamic mean field theory comes into play. So you already have seen many talks about dynamic mean field theory. The cluster extension of dynamic mean field theory is in spirit the same theory, but the quantum many-body problem on the lattice is replaced rather by an impurity of a cluster. So you don't have just a site, you have a cluster of sites, and this cluster of sites is embedded in a bath of non-interacting electrons, which mimics the rest of the lattice. And then there is a cell consistency condition that relates this effective cluster impurity model to the original lattice problem, like in classical DMFT. So I will not enter the detail about that, just to tell you that the difficult part is to solve this impurity problem, like in DMFT. So one can do many things. For instance, quantum Monte Carlo, I will show you something about later. What I'm usually doing, and most of the results of this talk are done with this method, is to use exact diagonalization, which replaces the non-interacting bath with a finite number of sites. So the impurity problem is a finite size system. However, the cell consistency condition that here I have not written helps to relate these finite sites to the infinite lattice problem. So takes care a bit of these finite sites and cell consistency. Now, what I get out from this theory? Well, as you have seen already many times, the thing we can calculate in these models is the Green's function. Now, usually the Green's function has a frequency dependence, and that DMFT does it pretty well. And also a k-dependence a priori. We are in two-dimensional system. K-dependence is actually very important. We have seen before that the Fermi surface was strongly k-dependent, right? So, and from the Green's function, I can extract spectral properties, so spectral function, which, for instance, can be related to the ARPES measurements I showed you before. What we have with respect to the single site is that we don't have just the local Green's function. We have all the propagator within the cluster. So in this case, I will have a next neighbor Green's function, and nearest next neighbor, it will be the diagonal one. With these essentially 3 function parameter, I can reconstruct a k-dependent Green's function. Of course, this is an approximation. This is not even exactly what we are doing. I didn't want to enter the details, so it's a delicate thing to do. As a matter of fact, this works well. If you think this as a truncated Fourier expansion, you would like to have as many as possible Fourier coefficients. So bigger it's the cluster, better is going to be your approximation. So it's a very well-defined problem. How good is, for example, the 2x2 plaquette, which truncates already at the 4th term is not there anymore. All right. So I show you right away some result in the normal state. This is our prehistory of cluster DMFT. And on the left, you have ARPES experiments from KM, Shen, and Armitage. And this is an all-doped cuprate, and this is electron-doped cuprates. And again, this is a quadrant of the Brillouin zone, so you should have the full Fermi surface here centered around the pi point. But the Fermi surface, at a low doping, disappears, breaks into arcs. This is true in the all-doped. Even in the electron-doped, you have the position of the arc is exchanged with respect to the all arc position, but is still present, this effect. And if you do cluster dynamic mean field theory on the 2x2 plaquette, you get, doesn't matter then how you actually, what do you do to extract the GK. In any case, you will get a strong modulation of spectral intensity and the formation of Fermi arcs, so like in the experiments. So this was a first good result that was telling us that we are, the method was giving some reasonable result.
So is there a whole Fermi surface, but there's just matrix elements that you don't see? Or
Oh, that's an excellent question. Let's just be patient a moment. I come to the slide where this is more clear. It's a very good question, yes. Before arriving there, I just want to say that it was anyway an issue. We are using few parameters to describe GK with a 2x2 plaquette. So the question, well, if you increase your cluster size, does this picture also, or is it fake due to the small dimension of the cluster? And people have been rushing over the years, the last years, to increase the cluster size. This was possible thanks to the development of better codes, namely the continuous time quantum Monte Carlo. Here I show you a result of my collaborator Shiro Sakai that has managed to increase the cluster size up to 16, so 4 by 4. And you see this arc feature. There is some fluctuation. For example, the NCA equalate is a little bit bad defined. But then, essentially, from the 2x2 plaquette to the 4x4, it doesn't change much. So this seems to be a rather strong feature, very stable with respect to the cluster size. And let me just say that many groups have been working on this kind of problematics, increasing cluster size and developing algorithms. I didn't cite all the papers in detail. That's the reason why I show you all the groups that, to my knowledge, have been, well, there are many more groups than this, but these are the people that is asking more or less the same questions which I'm posing today in this talk. So there is the work of Mark Jarella, is pioneering this cluster method that has done a lot of important results. It was the first to show the stability of the superconducting state. Then the group of Gaby Kotler and Ruggers that have developed, well, these are two cousin methods, cluster extension, the dynamical cluster approximation, and the cluster of cellular dynamical field theory. André-Marie Tremblay has worked a lot on these methods, giving a lot of contribution. And recently, I want to stress the work of Giovanni Sordi, which has used a code developed by Christian Aule and Ruggers. And they have very nice results. Perhaps I will talk about one of them later. In recent years, there has been also the great work of Andy Millis with Emmanuel Gould, which is a great developer of continuous time quantum Monte Carlo. And they have done a lot of nice work as well. There is also the group in École Polytechnique of Anton George. Olivier Parcollet has been also collaborating with Andy Millis and Michel Ferrero. And a work of my collaborator in Japan, Shiro Sakai, which was in the group of Masatoshi Mada, and now is at Riken in the group of Arita. So this is more or less all the people that is working on this kind of problems with DCA and CDMFT. So I will not, of course, go on all the citations, but let me just present the first result in the underdog case. This is a work done thanks to Shiro Sakai, who has developed the continuous time Monte Carlo. And we collaborated with a group in Periset who are Raman scatters. So we look in the detail at the structure of the pseudogap, thanks to the 16 cluster site. Now we start believe to what we were seeing. And we compared it with what is expected to be the gap in a D-wave superconductor. So for coming back to your question that you were asking me, how I should see this pseudogap, this is like Harpe's spectra, if you want, only calculated with CDMFT. And this is the antinode, and this is the node. And you see how is the spectra. There is a gap. So there is a peak that is formed already, but the peak is shifted to negative frequency here. So there is a gap at the Fermi level. And when we move from the antinode to the node, the peak moves and comes to the Fermi level. And at this point, you form the arc. So this is what the pseudogap is in cluster DMFT. All right. So in a D-wave superconductor, what we expect is to have nodal points, points in the diagonal of the Brouillard zone where the gap goes to 0. And so we say, well, many theories are based on the fact that the pseudogap has a similar shape. Now, let's look at our pseudogap in going from the antinode to the node. So from the antinode to the node, and this is the energy axis. So it's like Harpe's a bit. And you see that this is a quasi-particle band that touches the Fermi level in the nodal point. And the pseudogap is this more darker region. And you see that there is like a parallel, more fainted band that runs at positive energies. And the pseudogap is always there, actually. It's true that it's strongly reduced at this temperature, but if you manage to decrease the temperature, and here with this 16 cluster, we didn't manage because the continuous time Monte Carlo could not go to lower temperatures, but it's clear that there is still a gap. So the pseudo gap doesn't close in the node. The pseudo gap is still there, only shift to positive energy. So it is definitely a different structure for what we expect in a D-wave superconducting gap, where this should close, actually. Should not have a gap here. Also notice here that the gap is rather asymmetric. Now here it's very exaggerated with respect to reality, but a superconducting gap is particularly symmetric. You will have a band here, the first Bogoliubov band, and the band negative. And the minimum should be more or less in the middle. Here the minimum is clearly shifted up to positive energy. So the total gap is asymmetric. So the two don't look to be the same. Even if for some way not.
The line of blue points, what is that?
Sorry?
The line of blue points in...
oh, yeah, okay, this was for the article, is where is actually the minimum. Okay. It's for the reference in the article. Thanks for the question, yes. So what we said is that if it's true, and perhaps we can save it in some spectroscopy. Now, it's really difficult, because what we would like to see is to show that in the nodal point, there is still a gap in the spectra, even if it is not at the Fermi level. It's shifted a bit in energy to positive value. So the idea is that if you use Raman, Raman actually is a good probe, because, well, ideally one would like to use ARPES, but ARPES cannot assess the positive energy very easily. It's very difficult. And above all, cannot assess this so high energy. So we said, but perhaps Raman will be able to do that. Raman sends a photon into the system, so the electron will change from an initial state to a final state, and transition of this time are possible, where the electron in initial state is the lower band, and in the final state, when the photon goes out, is in the other band. So we should see this band structure in these ARPES. Now, the problem is that we would like to distinguish between antinode and node. Okay, this is possible with ARPES, which using different light polarization is actually probing different regions of the Brillouin zone. This polarization, the B2G setup, will probe more the node, the B1G, the antinode. And this is what they see. In the antinode, we have a clear, well-defined pseudo gap. And if you look at the Raman spectra here in the B1G that are probing the antinode, you will see that decrease in temperature, you have a loss of spectral weight. That loss of spectral weight is a signature of the pseudo gap. Now, in the B2G, should not be the case if there is not a pseudo gap. Well, it's known from many other members of the cuprate family, actually, that there is a small going down. If you look at 250 is the black curve, 150 is the green doesn't happen much. The red is, there is some loss of spectral weight. It's very small, but it's there. And the mercury components, I think, is even more evident, which are cleaner. So what we have done, we have calculated with linear response theory, starting from the Green's function, we extracted with DMFT the Raman response. And that is what we see also. Well, in the B1G, we have a loss of spectral weight. That is the signature of the gap, the pseudo gap. And the B2G2, well, if I start from the same temperature, first I have an increase of spectral weight. That's normal in a metal. When you decrease temperature, the Raman response increases because the scattering time reduces. The slope is proportional to the scattering time. But at the lowest temperature, the red curve, loss of spectral weight. And by the way, this loss of spectral weight happens at different temperature. It happens before in the antinode and later for a lower temperature in the nodal point. So this explains this even small but universal behavior in cuprates. So our claim is that this is a proof that, as a matter of fact, we have a pseudo gap which has a structure different from the wave. And then what will happen if you put superconductivity? Well, if one enters in the superconducting states, this is a calculation done at T0, what will happen if you have a D-wave gap is that the D-wave gap should have this shape, so you see states appearing inside the band of the pseudo gap. So this black area, that was my band of the pseudogap, this is the nodal point. Now it's doubled in length. So this is the nodal point. I open a symmetric two Bogoliubov bands. So I should see states reappearing inside the gap. And that's what I observe also in the Raman spectra. What was my pseudogap in the nodal point, so the green, the red, and the superconducting state, you recover spectral weight, which is, in our interpretation, coming from the fact that you put states into the pseudogap at the nodal point. So it seems to me a pretty consistent picture that perhaps we have something consistent. Okay, there is some work done also by Manuel Gula and Andy Millis, which is, the results are in agreement with our results, even if the interpretation is not the same. All right. Now, there is the second point I wanted to stress, but I will be very quick on this. Sorry, because I don't have time. This is mainly the work done by the student of Alain Sakuto, Siam Benhabib. So what they have done, and I really sketch, sorry, is that they took Raman measures for different dopings up to the overdoped side. Hopefully you see, because I see that it's not so clear. So this is underdoped, and this is overdoped side. And what they've noticed is that there is a huge increase, well, not huge, but a clear increase of the spectral intensity at the value of the doping here, which is this one where you have this peak, around 22% doping. So we are strongly overdoped. So this is unusual. So let me just say that it was a very difficult experiment because what they are getting is absolute measures. So the setup is really complicated. How much time do we have? 5 minutes. How much do you need? 10 minutes. 10 minutes, okay. All right? And they also can measure the loss of spectral weight. And this is this here, the pseudogap. This white region is the loss of spectral weight. And the pseudogap decreasing. And they find this magic point where the pseudogap disappears and the Raman intensity is maximal. Okay, this is very unusual. What is very unusual is that the Raman intensity then decreases again. It should be increasing all the time, the Raman intensity. But this is not the case. So with my friend Idran and Paul, so this is the detail of it, but we'll just skip it. We had an interpretation of this in terms of Lipschitz transition, namely in the Bisco compound, which has two layers, so a bonding and anti-bonding band. One band at 22% goes through a Van Hoover singularity, so a density of states which has a maximum, crossing the Fermi level. This can increase the Raman response, and rightly at this point. So we explain this in these terms. What is strange is that the pseudogap 2 disappears at that point. But superconductivity doesn't see this at all. But this is weird, that superconductivity, if our explanation of the Van Hoover singularity is correct, it's very strange that the superconductivity doesn't see the Van Hoover singularity, the pseudogap yes. So it's like we don't have more than explanation than this, but it's another indication that the two are quite different. That's the point. So this is the summary of this work. So this is just to say that even in the underdoped side, there are indications that the two are competing in some sense, and they are sensitive to different phenomena. Let me just say that for all what I have said, a scenario more likely is that where pseudogap is actually competing with superconductivity, even if, differently from the usual theories on a broken order, we don't need an order parameter. It's just the way you get into the close to the multi-insulating state. And it's via this, I don't know if to call it a transition from a metal, a rather normal metal, and this pseudogap metal. All what I've seen, all cluster methods agree. But there is some debate whether the transition is a crossover, a first order, a second order. On this, there is no still consensus, and people is working to understand this. Depends on the method, on the cluster size, and so on. I'll come back. The last thing I want to say is about the superconducting state. Of course, with cluster DMFT, we have studied the superconducting states already in early times. And what you see, in fact, is a dome, superconducting dome, which is a function of the interaction parameter U. This is U in units of T, of the open T. You see, it has a dome-like shape around half bandwidth. Around half bandwidth is also maximal, and then decreases for increasing U. Like to say, it seems like J could be the antiferromagnetic coupling, which scales like 1 over u, could be related to this strength of superconductivity. And for what I've shown you, the picture we have is that a pseudogap arrives to end some finite doping under the superconducting dome. And the result we get with our method, this I'm talking about our work with Shiro Sakai, is that actually there is a coexistence of, at lowest temperature, of pseudogap feature and superconductivity. I come right away to tell what I mean by that. Here, just to say that there is a nice work of Sordi, Giovanni, and in the group of André-Marie Tremblay that has very similar phase diagram. They included temperature, which we didn't do in this work. And they studied pseudogap and superconductivity. You see that it's very similar. In their result, there is a first-order transition. This I cannot say with my method. There's technical problems, I cannot say that. And it's coexistent between superconductivity and pseudogap has also been found in some ARPES, recent ARPES results on BISCO by Vishik and ZXChen. So what does it mean to have a superconducting state which coexists with the pseudogap? So this is a recent work I've been pursuing with Shiro Sakai and Professor Imada in Tokyo. Now, to understand what is happening to superconductivity, one has to look to the pairing function. Pairing function in BCS is just a constant. But in reality, it has a frequency dependence. I'm almost done. And it has an imaginary part. The imaginary part is related to the boson distribution. The boson, which in normal superconductors are phonons. So you expect an imaginary part which portrays the shape of the distribution of phonons, or bosons in the case. Okay, why is it interesting to have these bosons, or phonons, boson peaks? Because if you look at the Kramers-Kronig relation, a peak in the imaginary part could eventually boost the gap. If the peak is closer to omega 0. Closer it is, more the gap. And that is the main result we found. Look, this is normal state. This is in the antinode, the spectral function in the antinode. This is the pseudogap in the antinode. The pseudogap in the antinode is a peak in the imaginary part of the self-energy. Now, when we go superconducting, so these are lower temperatures, so we are decreasing the temperatures. This peak, the blue line, evolves, is more sharper because you go down in temperature, the quasi-particle. So it's like a pole. A pole will increase. It doubles because you have the gap superconducting opening, so you are two Boguliov branches. But what was interesting is that if you look at the imaginary part of the self-energy, which is your pairing function, it also has peaks in the superconducting state, and the peaks are exactly the same. We checked it for many temperatures, many doping. The frequency is exactly the same. So the peak that is creating me the depression of spectral weight and the pseudogap in the normal state is smoothly connected to the peak in the pairing. So the shape of the pairing function is strongly dependent on this peak. And this is the last slide I have. So just to say, this is work in progress. Actually, we have a preprint already out if you want to look more in detail. You pick an imaginary sigma, it means a push-up of the gap. This peak is actually the same that is creating the pseudogap. So in some sense, the pseudogap and superconductivity looks competing for same electrons. But on the other hand, the presence of the peak is in the self-energy, so the presence of the pseudogap is shaping the self-energy, the anomalous self-energy, and this can boost up TC. Of course, the same self-energy, once one looks at the gap function, which is the one you look in the spectral functions, in the spectra you take in experiments, there is like a z that has to multiply this anomalous self-energy, which depends on the normal part of the self-energy, which has the peak. So this guy, if this one goes to 0, close to the mode transition, this would destroy the gap. So this comes back a bit to the idea of Anderson, actually. So as a matter of fact, this is the end of my talk. This poses more questions than given answers. The structure of the pseudogap looks different, but in some way seems to help superconductivity. And in the way that is not too far from what Anderson, if Anderson was talking about preformed pairs, if you want, It's not far from that, this fact that the peak is appearing in the self-energy. Now, this is my conclusions. So I hope to have shown you good evidence, at least for Hubbard models in 2 dimensions, that you don't need broken state to explain a pseudogap. It doesn't mean that in reality you will not have a broken state. Ultimately, these broken states that originates from the pseudogap could help superconductivity. This is possible. Just talking about this Hubbard model. The pseudogap superconducting gap looks competing for the same electrons, and they have different shapes and different response to different solicitations. In the overdoped and underdoped side, we have compared with Raman. On the other hand, the origin of the pseudogap seems to shape a lot superconductivity as well and boost up TC. So at the same time, this competition might be LT and LT for superconductivity. Okay? So voila, this is the last thing I wanted to say. And that's the end of the talk. There is still work to do and work in progress on this, hopefully.
Thank you very much. I think we're a little behind, so we have time only for a couple of questions.